So what's it like to use geometry by construction? I'm going to do everything in Sketchpad, and we're going to be in Geometry Sketchpad, and we're going to make a few things. So Euclidean space is all this stuff, all out here and in here. But inside this unit circle, inside this circle of Euclidean radius 1 is hyperbolic space. And hyperbolic space does not include the boundary circle. So here's what I'm going to do. I'm going to make a hyperbolic circle centered at the point O, and a hyperbolic circle is also a Euclidean circle. So there's a hyperbolic circle. And I'd like to make another hyperbolic circle that has the same area as this one. Let's make this guy the circle that we care about. So this outer circle is the boundary of the space, and this is the circle whose radius is OB. So it's radius OB. Now, I'd like to do the steps. Here's the way the construction goes. I'm doing a Euclidean construction. I'm constructing a perpendicular line. That's a Euclidean perpendicular line. It's not a hyperbolic line. But if I finish doing this, so I'm going up to that point of intersection, then I'm going to construct another perpendicular. This from the book are the steps of constructing a line, a point that is the inverse of point B. So here's the point B inverse right there. And that's a Euclidean construction. Well, we can keep calling it C. That's okay. We'll just call it C. But that's the inverse of point B. The meaning in Euclidean is the Euclidean distance OB times the Euclidean distance OC is equal to the square of this radius. But we don't care about that unless we're going to prove something in Euclidean about these structures. But here's the rest of the construction for a circle. I'm going to make a circle that is congruent to circle with radius OB. I'm going to make a circle that has the same size in hyperbolic, but it won't be centered at O. It'll be centered at B. So here's how this goes. I'm now going to make a segment that goes from B to B inverse, and I'm going to construct its midpoint. And now I'm going to make a circle that is centered at that midpoint and goes through B and C. This is actually a hyperbolic line. I'm going to color it red to show that it's a different kind of animal from the other kind of curves. This guy in hyperbolic space, any circle that's perpendicular to the boundary circle is a hyperbolic line. And we're using a result that if you have a Euclidean circle that goes through a point and its inverse, then that Euclidean circle is perpendicular to the circle of inverse, in our case, the boundary circle. So this red guy is a Euclidean circle, but it's also a hyperbolic line. The part that's in the space, this arc, is a hyperbolic line. Now I'm going to draw a Euclidean segment, and I'm going to make a circle that is that goes from O to this point. So I'm going to get that point marked. I'm going to make this segment. Let's make that a different color so it stands out. How about dark purple? All right, now I'm going to construct the midpoint of that segment, and I'm going to make the following circle. I'm going to start there, and I'm going to go here. Now that's not a hyperbolic line, so I'll make it another color of, let's say another color of green. Now that circle is a hyperbolic circle. This guy right there, let's make him even thicker so you can see him. That circle, which has its Euclidean radius at this point E, I'm going to call it point E. That's its Euclidean center, but its hyperbolic center is point B. Let's see why. Well, let's see what we got here. I've got a hyperbolic circle, and here is, let me label this point over here. The Euclidean radius, EK, is the same size as the Euclidean radius, OE, because E is the Euclidean center. But if we look at it as a hyperbolic entity, I have a line that is perpendicular to this green guy. It's perpendicular to that green guy, and it's a hyperbolic line. So that means that this thing, this point B, has to be the hyperbolic center of this green circle. So if that's the hyperbolic center, then BK is a radius and BO is a radius. These are hyperbolic radii. See, in hyperbolic, you can have two kinds of line. You can have this curved arc, or you can have diameters. They have to go through O or lie on O to be a hyperbolic line or segment. So I have the hyperbolic segment BK, and I have the hyperbolic segment BO, and they are congruent because they're radii of the same hyperbolic circle. So that means this little green circle right here has the same hyperbolic area as this neighboring circle over here. They have the same hyperbolic area. So that's pretty cool. And that's the kind of stuff that you can do in this book of mine, Geometry by Construction. You make the things you're talking about, and the only thing that we didn't prove was that this red circle is perpendicular to the green circle, but I can leave that to you as something that you try, because all the information you need to prove that they are perpendicular is there. But you would do a Euclidean proof to show that these two circles are perpendicular. You would use something about inverses of points. All right, so that's what it's like, you guys. Try buying the book. It's cheap. It's a fun book.